let's discuss the molecular orbital diagrams or the energy level diagrams of the elements belonging to second period, that is from lithium to neon. Okay, now energy level diagram for hydrogen molecule and helium molecule we have seen in the previous video. So today we'll discuss the remaining energy level diagrams. Now lithium molecule, it is made up of lithium plus lithium, and the electronic configuration for lithium is 1s2 2s1. So the energy level diagram will be having two, the diagram for 1s and the diagram for 2s. Now from here to here your energy increases. Now this is 1s, this is 1s, this is first lithium atom, this is second lithium atom. Now first addition sigma 1s and then subtraction sigma star 1s. Okay, now add these. Likewise we can make for 2s also. Follow symmetry rules while making the diagram. This is 2s, this is 2s, this is sigma 2s and this is sigma star 2s. Now the configuration is 1s2 2s1. Now 1s2 2s1 for first lithium atom, for the second lithium atom. Now 2 electrons here, 2 electrons here. How many electrons are there? 4. So they will occupy bonding and anti-bonding. So 1, 2, 3, 4. Okay, so always remember, whatever electrons are present in the atomic orbitals, the same electrons occupy molecular orbitals. So 4 electrons will come here. Now 1 and 1, how many electrons are there? 2. So they will come here. Okay, now anti-bonding will not be filled because only 2 electrons are there. Now write the electronic configuration. So it is, right from the beginning, sigma 1s2, sigma star 1s2, sigma 1s has 2 electrons, sigma star 1s has 2 electrons, and sigma 2s2. Now what we can do, now this configuration is of helium, so we can shortcut this configuration and we can write for this KK. Now what this KK indicates? K shell, that the first shell is fully filled. Okay, so this is a way to write electronic configuration. Now second thing is bond order, half into, now how many bonding electrons are there and how many anti-bonding are there. So how many bonding electrons are there? 2 and 2, 4, and how many anti-bonding are there? 2. So it is 1, means lithium has single bond. And the third is magnetic nature, filled, 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 paired, paired, paired. All the electrons are paired, so the molecule is diamagnetic. And we have seen in the previous video what is the meaning of diamagnetic, which is repelled by magnetic field. So likewise we can also make the energy level diagram for beryllium molecule. Now let's see. Now this is the diagram for beryllium molecule. Okay, now 1s2 2s2 means this block will be fully filled and this block will be fully filled. Okay, now let's find out bond order. Half into bonding minus anti-bonding. Now how many bonding electrons are there? 2 and 2, 4. And how many anti-bonding are there? 4. So 0. It means the molecule does not exist. So when the bond order is 0, the molecule does not exist. So no need to write its configuration and finding out its magnetic nature, because the molecule does not exist at all. Now the remaining molecules are B2, C2, N2, O2, F2 and Ne2. The energy level diagram for these 3 molecules is similar and the energy level diagram for these 3 molecules is similar. What is the difference in them? That we'll discuss. So first we'll make the energy level diagram for B2. Now let's discuss it for B2 molecule. Okay, now B2 is this boron atom and this boron atom. Now what is the configuration of boron? The configuration of boron is 1s2, 2s2 and 2p1. So I have made the diagram for 1s, this is for 1s, this is for 1s, and this diagram is for 2p. Now why the diagram of 2p is like this? Because there are 3 p orbitals, 2px, 2py and 2pz. 3 here, 3 here. So total 6 will be formed. So this is 1s, this is 2s, and this is 2p. This is 1s, this is 2s, and this is 2p. Now it will be sigma 1s, sigma star 1s. It will be sigma 2s, sigma star 2s. Okay. Now there is no problem in writing these. But how to write for 2p? Now we know that there are 3 p orbitals, 2px, 2py and 2pz. 2pz always forms sigma bonding and 2px and 2py form pi bonding. So the orbitals which are together, they are of same energy. So one is pi 2px and another is pi 2py. These are degenerate. The orbital which is alone is sigma 2pz. Now the corresponding antibonding counterparts. So pi star 2px, pi star 2py and sigma star 2pz. Okay, now you can see bonding are lower in energy, antibonding are higher in energy. Now fill the electrons. 1s2, 2s2 and 2p1. 1s2, 2s2 and 2p1. Okay, now this and this will be fully filled. Okay, like this. Now there are 2 electrons. Now these 2 electrons will occupy here. First this pi orbital will be filled because it is of lower energy. Okay, now we'll follow a rule, that is Hund's rule. Pairing does not occur until all the orbitals are singly occupied. So one electron will come here and one electron will come here. Okay, so this is a way to fill the 2p boxes. So we'll write the electronic configuration. Now how to write? For this I can write kk. Okay, because this configuration is of helium, that is 1s or shell, first shell is fully filled. Then sigma 2s2, then sigma star 2s2. Now it is done. Now pi 2px is having 1 electron equal to pi 2py is having 1 electron. Now why this equal to sign is there? Because in others comma is there. Here equal to sign is there because the 2 orbitals are of same energy. Bond order. Half into bonding minus anti-bonding. Now how many bonding electrons are there? Now 2 bonding to anti-bonding cancelled. 2 bonding to anti-bonding cancelled. So if you want to calculate bond order, no need to count these. We can neglect these 2 because they are 2 bonding to anti-bonding already cancelled. So bond order we can simply calculate it from 2p also. So how many bonding electrons are there? 2 minus 0. Anti-bonding are not there. That is 1. And now magnetic nature. Now these are filled, paired, but these 2 are unpaired. So the molecule is paramagnetic. Okay. So this is the energy level diagram for B2 molecule. Likewise, if I want to make it for carbon, that is C2. So I will make changes here only. So this is C2. So 2p2 now. Okay. Now 1s and 2s will remain same. There is no change in the diagram for 1s and 2s. Okay. After beryllium, they will be fully filled. Now 2p2. 2p2 means 1 electron is here more and 1 electron is here more. 2 here and 2 here. Now total 4 are there. 2 and 2 4. So they will be paired like this. Okay. So pi 2px 2 and pi 2py 2. This is the change. Now bond order. No need to count these. Half into. Now how many bonding electrons are there? 4. So bond order will be 2. Okay, and magnetic nature, paired, 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 paired. So the molecule is diamagnetic. So this is the energy level diagram for C2 molecule. Okay. Now the next molecule is N2. Now the diagram for B2, C2 and N2 are same. So in this diagram only I will make the change. So for N2, suppose my molecule is N2. So 1s2, 2s2, 2p3. Now 2p3 means one more electron will occupy. Okay, so like this. Now what is the change? No change in 1s and 2s. 3 and 3, 6. So 1, 2, 3, 4, 5 and 6. Okay, now in the configuration also a change will be there. Okay, now equal to sign is there between these two because these two are together. Now sigma 2pz 2. Now bond order half into 6 minus 0. 6 are there, so bond order is 3. It means nitrogen and nitrogen has triple bond, and this is true also. And magnetic character, it is diamagnetic. Now let's discuss this for O2 molecule. O2 means O plus O, and what is the configuration of oxygen? 1s2, 2s2, 2p4. Okay, now this is 1s, 2s, 2p, 1s, 2s, 2p, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Now you can see there is change in the diagram. There these two were down and this was up. Now why this change is there? This change is there because up to nitrogen, the difference between 2s and 2p orbital is small, so they can interact. But after this, the difference is more. Okay, and this is beyond the discussion in 11th and 12th class. So simply you have to remember that after nitrogen, that is from oxygen, sigma 2pz is of lower energy. Now these two are pi 2px and pi 2py. Now this is anti-bonding. There is no change in the upper part. You can see upper part is same. Only the change is in the bonding part. Sigma star 2pz. Now 1s2, 2s2, 2p4. Now 1s and 2s will be fully filled. Okay, so no change. Now 4 electrons here, 4 here, so total 8. So how we will fill? 1, 2. First it will be fully filled. Okay, 3. Now third will come here. 4. So 1, 2, 3, 4, 5, 6. 6 I have filled. 7 and 8. Now anti-bonding orbitals will start filling. Now what is the electronic configuration? Now kk for this, sigma 2s2, sigma star 2s2. Now sigma 2pz2, comma pi 2px2 barabar pi 2py2. Then pi star 2px1 barabar pi star 2py1. Okay, these have equal sign because they are having same energy. Bond order half into. Now neglect these two. 6 minus 2, that is 2 double bond. And what is magnetic nature? Now these two are unpaired electron, so the molecule is paramagnetic, and oxygen is paramagnetic in nature. It is attracted by magnetic field. Likewise, in the same diagram we can make for fluorine and neon also. Okay, now fluorine is 2p5. 2p5 means two more electrons will be added here. And neon is 2p6 here, 2p6 here. So the entire diagram will be fully filled. So try to make the diagrams for F2 and Ne2 in your copies. So we have discussed the energy level diagrams for the molecules starting from hydrogen to neon. Okay. Now, how to make energy level diagrams for molecule ions. Now what is the meaning of molecule ion? Like this. The molecule has a charge. Like this. So how to make the energy level diagram for these molecular ions? So we'll take one example. Suppose I want to make the diagram for H2 plus. H2 plus means one is H and second will be H plus. Now H means the configuration will be 1s1 and H plus will be means the configuration will be 1s0. So now join them. Now this is 1s, this is 1s, this is sigma 1s, this is sigma star 1s. Now this is having one electron and this is not having. So the single electron will come here. Okay. So what is electronic configuration now? Sigma 1s 1. And what is bond order? Half into 1 minus 0, that is 0.5. And the molecule is paramagnetic. The bond order is 0.5. Now we have made the MO diagram for H2 molecule. For H2 molecule, the bond order is 1. Now for H2 plus, the bond order is 0.5. This bond order is directly proportional to stability. So if it is asked which is more stable, definitely H2 is more stable. Likewise, we can compare the stabilities, bond enthalpies from this bond order data. Suppose I want to make the diagram for O2 plus and O2 minus, and I want to compare these two. Now O2 plus means O and O plus, and O2 minus means O and O minus. O means 1s2, 2s2, 2p4, and O plus means 1s2, 2s2, 2p3. Here O means 1s2, 2s2, 2p4, and here it is 1s2, 2s2, 2p5. So you can see that there is no change in the electronic configuration of 1s and 2s. The change is only there in 2p. So what I will do, I will make the 2p diagram only. This is for this. Now 2p4 and 2p3, total 7 are there. Here 2p4 and 2p5, total 9 are there. So how to fill the electrons? Now how to fill the electrons? So 4 plus 3 7, so 1 2 3 4 5 6 and 7, and here 1 2 3 4 5 6 7 8 and 9. Okay, now calculate the bond order. Half into 6 minus 1, that is 2.5, and here the bond order is half into 6 minus 3, that is 1.5. Now which is having greater bond order? This one. It means O2 plus, I can write here, O2 plus is more stable than O2 minus. Now a question is there, arrange these 5 species in the increasing order of stability, increasing order of bond dissociation enthalpy, and increasing order of bond length. Okay, now this is O2, O2 plus. Now O2 minus is known as superoxide ion, then O2 2 plus, and O2 2 minus is known as peroxide ion. So how to solve this question? If we want to get the order of stability or bond enthalpy, first we have to calculate the bond orders. Now this is the standard, O2 is equal to O plus O. Now what is the bond order of O2? Half into 6 minus 2, that is 2. So simply learn the bond, how to find out bond order for O2. Now O2 plus is there. O2 plus means one electron we have to remove. So from which we will remove the electron? Definitely from the outer one. Outer one means the anti-bonding one. So half into 6 minus 1. Because O2 plus is O and O plus. One electron you have to remove. So that you will remove from the anti-bonding part. So 6 is the bonding part. 2 is the anti-bonding. So one electron we have removed. So bond order is 2.5. Likewise O2 2 plus. Now 2 electrons we have to remove. So these 2 anti-bonding electrons will remove. And 6 minus 0 it is 3. O2 minus, it is O and O minus. One electron we have to add. So half into 6 minus 3, 1.5. And O2 2 minus is O and O2 minus. So 6 minus 4, because 2 electrons we have to add. So the bond order is 1. So we have calculated the bond orders. Okay, means no need to make the MO diagram. Simply if you know how to find out the bond order for O2, this is the standard one, we can calculate the bond orders for the similar species. Now we know the relation bond order is directly proportional to stability. Bond order is directly proportional to enthalpy, bond enthalpy. And bond order is inversely related to bond length. Okay, so these are the three relations that we know. Now first we'll arrange them in the increasing order of bond order only. Now which is having least bond order? O2, 2 minus. Okay, 1, then 1.5, that is O2 minus, then O2, then O2 plus, and lastly O2, 2 plus. This is the increasing order of bond order. Okay. Bond order is directly proportional to stability. So the same will be the order for stability. Okay. So what is the order for stability? Same. This is the order for stability. Bond order is proportional to bond enthalpy. So the same order will be for bond enthalpy. This is bond enthalpy. And lastly, we have to find it for bond length. Now what will be the bond length? Since this is inversely related, so the reverse order means it is like this. Exactly reverse order. So this is for bond length. So for finding out these, first we have to calculate the bond orders. So we discussed the last concept of bonding, that is molecular orbital theory. Now the last topic of this chapter is hydrogen bond. Okay, H bond. Now what is hydrogen bond? It is a special type of bond which is found only in limited number of molecules, and it does not involve any electron sharing or electron donation. Okay, means a bond which is formed without electron sharing or electron donation. Now how it is this? Hydrogen bond is found only in those molecules which have hydrogen atom. So the first condition is hydrogen must be there, and this hydrogen is attached either to fluorine, this hydrogen is attached either to oxygen, or this hydrogen is attached either to nitrogen. So hydrogen bonding is found only in these three special cases. Hydrogen should be attached to fluorine, hydrogen should be attached to oxygen, or hydrogen should be attached to nitrogen. Because fluorine, oxygen and nitrogen are the three most electronegative elements. So these are the three electronegative elements of our periodic table. Now what will happen? Suppose hydrogen is attached to fluorine. This is HF molecule. Now what will happen? The electron sharing is there. This is a covalent bond. Since fluorine is more electronegative, so what this fluorine will do? It will attract the electrons towards itself. Polarity will appear. This will be del plus, this will be del minus. There will be generation of partial positive and partial negative charges on hydrogen and fluorine. And this is only because of more electronegativity of fluorine. Now this is first molecule. Likewise, there will be second molecule. Now here also del plus and del minus. Now what will happen? The negative end of one molecule will attract the positive end of another molecule, because the molecule does not exist alone. In a container, so many molecules of HF will be there. So this negative will attract the positive end. Okay, so it is HF, one molecule. This is HF, second molecule, by a weak force of attraction. And this weak force of attraction is shown by a dotted line, and that attraction is known as hydrogen bond. Now you can see no electron donation, no electron sharing is there. There is a simple attraction. And why this simple attraction arises? Because of the electronegativity difference. One atom is highly electronegative and another atom is very less electronegative. Hydrogen bond is always shown by dotted line. And it is a very, very weak bond. It is not as strong as your covalent bond. It is of the strength of 1/10 of a covalent bond. So it is very weak bond. We can easily break this hydrogen bond. So how to define it? when hydrogen is attached to more electronegative atoms like fluorine, oxygen and nitrogen. This is an important point. This is a limitation. Okay, it is not found in each and every molecule. The more electronegative atom acquires partial negative charge and the hydrogen atom acquires positive charge. Now the force of attraction between positive end of one molecule and negative end of another molecule is known as hydrogen bond. And why it is known as hydrogen bond only? Because the presence of hydrogen is required here. Okay, now let's discuss some examples. The first is HF, like this. Okay, the second example is water. This is the structure of water. Now del plus, so it will be 2 del minus, like this. Now it will be attracting. Okay, and the third example is ammonia. Ammonia is this. So del plus, del plus, del plus. So it will be 3 del minus, like this. Okay, it means hydrogen bonding is formed between two different molecules, and because of this hydrogen bonding there is a weak attraction between the molecules which keep the molecules closer. And you know one interesting fact, that because of this hydrogen bonding only water is liquid at room temperature. So if hydrogen bonding was not there, water would be a gas. Okay, so because of this hydrogen bonding, what happens? What are the consequences? Okay, physical state changes and boiling point increases, because hydrogen bonding means extra force of attraction. So the boiling point of molecule will increase. The boiling point of water is 100 degrees Celsius. It is exceptionally high boiling point because of this H bonding only. So these are the influences of hydrogen bonding. Okay, association of molecules, high melting point and boiling point, and physical state also. And sometimes hydrogen bonding also influences the solubility. Okay, only those compounds are water soluble which can make H bonding with water. For example, alcohol dissolves in water because alcohol makes H bonding with water. That we'll discuss in higher class. Now there are two types of hydrogen bonds, intermolecular and intramolecular. Intermolecular is formed between two different or same molecules. So two different molecules or same molecules will be there. For example, one HF and another HF. Now this is one water molecule and one alcohol, HOR, this is alcohol. So you can see hydrogen bonding is formed. Okay, because both have hydrogen and oxygen. And what is intramolecular? Between two different groups of the same molecule. Now this is a single molecule. One group is OH and second group is NO2. Okay, this is basically orthonitrophenol that we are going to discuss in our organic part. Now this group is having H and the next group is having O. So there is formation of H bonding. So this was all about a brief introduction of hydrogen bonding, because this hydrogen bonding has wide applications in chemistry, especially in the organic